One of the motivating examples that we gave for string matching is using something like a text editor. So when we are editing text, then we are generating text, and as we are generating the text, we are looking for some other patterns to make changes. But quite often, search happens in the context of a piece of text that is fixed. So for instance, you might be trawling through a large body of work by a single author, like the collected works of Shakespeare, or you might be in an organization which has a large body of reference manuals. Or in another example that we have frequently cited, you might have genetic data for some organism or organisms that you want to search in. So this is a more typical situation where you have a body of text which is more or less fixed, but this text is going to be searched repeatedly. So what would we search for? For instance, if it is Shakespeare's plays, then we might have a quotation that we want to search and find which play it came in and who spoke it. So this is a typical example where a number of quotations are very famous from Shakespeare's plays. So when we come across one, we want to know, is this a quotation from Shakespeare or not? So we query this text which is fixed. Similarly, if you have some question about something to do with the operation of your organization or your machinery or whatever, you might want to query the reference manual for a part number or a process. And finally, when you have a gene sequence for an entire organism and you want to find out if a particular pattern is there, you might want to query this, or you might have a database of such genetic material from a number of organisms and you may want to look for it across this database. So in all these situations, the difference is that we are searching for a pattern repeatedly in a piece of text that is not changing at all. So we could hope, since the text is not changing, we could hope to do something with the text, that is to process the text and make it more efficient to search for this pattern, so that the cost of searching for the pattern does not depend on the text at all. If you remember, when we did things like Knuth, Morris, Pratt and so on, we said that we would do things in time order n plus m, where n was the length of the text, right, and m was the length of the pattern. Now if we have a fixed pattern, we would like to make this dependence on n, or rather a fixed piece of text, we would like to make this dependence on n go away. We would like the search to be only proportional to the length of the pattern. So how can we do this? So one way of doing this is to record the words in our text in a special kind of data structure called a trie. So the word trie actually comes from information retrieval. So it is hidden inside the word retrieval. So as you can imagine, in retrieval it's pronounced tree, and that's how the original inventor of the trie intended it to be pronounced. But since we use trees all across the place, TREE all across the place in computing, it has become conventional to call this data structure a trie. So it is a special kind of tree, but to distinguish what special kind of tree it is, we call it a trie. What about information retrieval itself? Well, information retrieval is the traditional subject of this kind of search that we are talking about. You have a body of text and you want to search for it. So for instance, this has been the case with libraries. For instance, if you are looking for a book in a library, or in the legal profession, you have cases and cases which have taken place in the past, and when you come across a new case, the lawyers would like to look for precedents. So they would like to search for certain earlier cases which have similar features to the current case. So information retrieval is a traditional subject which goes back far beyond modern computing. But in the modern context, whenever we query a search engine, what we are doing is information retrieval. We have a body of text, namely all the text on the internet, and we are searching for a pattern against this. Now of course this body of text on the internet is not a fixed piece of text because it keeps changing. People keep adding and modifying documents. But what search engines do is they try to index or pre-process these documents once in a while, so that effectively when you make your search, it is not looking at the current state of the documents, but at the state of the documents as they were when they were indexed. So it's as though the internet is a fixed set of documents and you are searching in that. So all of these fall under this broad category of information retrieval, and the trie was invented to deal with that. So what does a trie look like? It's a special kind of tree, as we said. So basically it has a root. So it is like our search trees and heaps and other trees that we have seen. And at every node other than the root, we have a letter from our alphabet sigma. Now one of the properties is that if we look at any node in the tree and we look at the labels of its children, remember that each node is labeled by a letter from sigma. These labels are all going to be different. So you will not have two children with the same label. So that is the property of a trie. So on the right we see the trie corresponding to a set of words. So remember, if you have a fixed text, you can decompose it. If you are only, let us have a simple situation where we are looking for words in this text. We want to do a keyword search. So we are only interested in recording, in some sense, the dictionary or the set of words that this text contains. So suppose this text contains these words: bear, bell, bid, bull, buy, sell, stop and shock, and stop and stock. So what we have is a kind of clever organization of these words in this tree form, so that if you walk down and follow any path, so for instance if you follow this middle path, then you read off the word bid, which is one of the words in your dictionary. Okay. If you follow this path, then you read off the word buy, which is also a word in your dictionary. So every maximal path in our trie denotes a word in the dictionary. So here for instance we have stop, and here on the right we have stock. Now the fact that children have distinct labels means that essentially we keep prefixes together so that we don't have one path per word. So all the words starting with B pass through this node B, all the words starting with S pass through this node labeled S. Now buy and bull start with B and U, so up to here there is a common prefix and then they diverge. So in this way a trie compactifies the words by sharing the prefix as far as possible and then taking us to the end. Now there could be some ambiguity about where a word ends. So we saw this, if you remember, when we did Huffman coding, we talked about the fact that when you are decoding a code, you need to know where the symbols should be broken in order for us to be able to recover the letters one by one. So we said that one of the things that we wanted a code to satisfy is that no encoding of a letter is a prefix of another letter. So we need a similar property here. We need to know where the words end so that we know whether a word is there or not. Right? So for instance, in this particular thing there is no possibly sensible word, but you might ask whether the word BEA is a word in our set or not. Okay? But the way we do it in this particular thing is to effectively add an end of letter symbol. So if you notice this trie here, just to make things simple, we have denoted the last letter of every word by a square rather than a circle. But in practice what this means, and we will see later, is that there is actually one extra symbol hanging off each of these. So each word is completed by adding a dollar to it or some symbol which is not in my original alphabet sigma, and this signifies that the word is finished, so that if I see a prefix of a word, then a trie will report that it is not a valid word, it is just a part of the word. So we typically build a trie, as we said, from a set of words. So this set of words, capital S, has some subset of words. So in this particular case, if you remember, we had about 8 words, and totally we have some n symbols across these words, right? So if you look at this particular thing, we have 1, 2, 3, 4, 5, 6, 7, 8 words, and we have 4 plus 4 plus 3, 11, 15, 18, 22, 26 and 5, 31 letters across these 8 words. So now to search for a word, as we said, we follow the path. So for example, if we look for the word bell, then we just read off the path. So the first letter is B, so we must go this way. The second letter E, so we must go this way. The third letter is L, and then we come here, and then we have implicitly hit this dollar, right? So if we finish the word and we have reached a node whose success is a dollar, then we have found it. On the other hand, if we look for a word that, for instance, is not there at all, then we would start with B, U, L, and now we want to look for a successor node labeled K, but there is none, so we get stuck here. So this is one way in which we can fail. Right? The other way in which we can fail, as I said, is that we will complete reading the word, but we don't reach a leaf node. That is, we don't reach a node whose successor is dollar. So this is how we search for a word. Okay? So now, if we look at this, what can we say about this trie? So first of all, each path is a word in my set S. So obviously the longest path is the length of the longest word, right? So if I take all the words in S and I take the length of them and I take the maximum, then the longest word will represent the longest path. So every word is explicitly represented as a path in my try. Of course, because each node has at most one label for each letter as a child, a node cannot have more successors than there are number of letters in my alphabet, right? So this, for instance, has 3 successors, but in my alphabet here, if this is my English alphabet, even in this set of words, we have used 8 or 10 words. So we could not have more than 26 successors if we are using lowercase English letters or other thing. But not everything will have all successors. So B has 3 successors here. This BI has only one successor because there is only one word with prefix BI. Similarly, STO has 2 successors because we have both stop and stock and so on. Now each leaf in my tree corresponds to a word. Remember, each path is a word and each path will terminate in a unique leaf. So every leaf is a word. And how many words did I assume? We have small s words in our set that we started with. So the number of leaves in our try is going to be small s. Now in the worst case, we don't have any sharing of prefixes. Supposing our set just consisted of maybe bear and say cell. If this is my set, then my try would have looked like follows. I would have had a B here, I would have had an S here, and then I would have had a EAR and an SELL, right? So I would have had one root node, plus I would have had one node for every letter in every word in my set. And of course, I would have had the dollar nodes, which I have not counted. So I would have had 2 dollar nodes. So I would have n plus 1 nodes at most. Now in general, it's not going to be n plus 1. So for instance, here, remember that we said that this had, I think, 31 letters. So we could have had 32 nodes, not counting the dollar, but we don't have. We have much less than 32. If you look at this picture, we have 5 plus 6, 11 plus 6 plus 5, 16. So we have about 21 instead of 31, right? So because of the sharing of prefixes, the try can be smaller, but it cannot be any worse than the total number of letters in the set that you are trying to encode. So this is a vanilla try, right? The vanilla try just keeps track of the words that we have. Now you could use this try to keep more information. So supposing these words were actually drawn from a sentence rather than a set of words. So here is the sentence: see a bear, sell stock, see a bull, buy stock. So in this we have positions, right? So we can have 0, 1, 2, 3 and so on, right? So what we might want to do is not just record the words in my try, but also record where they occur in my try. So if we look, for instance, for the word bid, it says it occurs at positions 47 and 58. That's because you see 2 occurrences of bid here. We see a bid here, and where else do we see a bid? So maybe it's not in 2 occurrences. So maybe it is buy, which should be in. So let's see another word. So maybe that's a mistake, but let's see a word like see, for instance. So see occurs twice, right? So the first time occurs right at the beginning. So if you look at SEE, right, it occurs at position 0 and it occurs at position 24. So in this way, what we can do is we can maintain, so when we reach the root node, instead of just saying we have found the word, we can store information at that point. So it becomes like a function, right? So it becomes a function where the words in my text collection are the keys. So this is a bit like a dictionary stored in a very different way. So the keys are my paths in this try. So each key is a word in my text, and the value that I store depends on what I want. So in this particular try, I am trying to store the positions of the words as they occur in this given piece of text, so that not only when I find a word do I know it is there, I also know where all it occurs. Right? So you can think of this like, as I said, a dictionary, and a dictionary indirectly is implementing, if you remember, a hash function. So a try can be seen as a clever type of hash function, where the clever representation of a hash function, where the keys actually happen to be words. So one advantage of a try we know is that every path is unique. So no 2 words will lead to the same leaf. So there will be no collisions. So in that sense, it is simpler than a hash function, where you compute some value of the key and you might end up with 2 different keys producing the same output, and then you have to resolve this conflict. But on the other hand, the difference that we have with a try is that we are explicitly keeping all these nodes. So the penalty of not having conflicts is that we are creating as many leaf nodes as there are elements in our set of keys, as many words as we have. So therefore, a try will be much more space expensive than a hash table. But it is another way of using a try which is to just use it as a way of keeping these key value stores, where you store the values at the root or at the leaf nodes where the words terminate. So let's look at a very simple implementation of tries in Python. So here is a Python class for try. So what we are going to do is we are going to keep this tree. So initially we start with a root which is an empty. So we are going to maintain these children as keys in a dictionary. So each node will be a dictionary and its entries will point to its children. So initially I have a root node which is the empty dictionary, right? And now I can start it off with a set of words which by default is empty. But what I will do otherwise is for every word in the set, I will add it to my try. So that is this add function, right? So the add function inserts a new word into the try. So what does it do? It starts with the root, right? Then it appends this special symbol dollar to the word. And now it walks through this word, including the dollar, right? So it starts at the root and it looks for whether the first letter in my word is a key or not. If it is a key, it goes down that way. So if there is already a node, say my word is able, right? And my tree already had A, B, right? Then what we would do is that we would actually walk down to A, then we will walk to the B key of A and so on, right? And then finally, when we don't have any key, then we will create a new key, right? So that's the idea. So that's how we add a word to this try. And now when we want to check for a word in the try, remember that we follow the path, right? So there are three possibilities. The first possibility, the good one, is that I reach the last node and I reach a dollar after that. So I can say yes, this word exists, right? Otherwise, I might reach a situation where midway I get stuck and then I can say no, the word does not exist. The third possibility is that I reached midway and my word ended, the word I am looking for S terminated, but it is not a complete word as far as try is concerned. So we return three values, true, false and none in this case, right? So I start at the root and I start walking down. If at any point, so in add, when we did not find something, we added the key. So here if it is not in the keys, then we return false, saying that we have reached a point where we got stuck, right? Otherwise, we go to the next key and we keep going down, right? Finally, if we find that at the end we have reached a situation where the node that we are pointing to has dollar as its next key, then it means that we have reached the end of the word, we can return true. However, if we have come out of this loop, we have finished processing the tree, we have the word that we got and we did not bail out with a false, but we did not reach a dollar. So dollar is not in the keys, then I will return none. Okay. So this is an implementation, a simple implementation of building a simple try and querying it. So an interesting and important extension of this notion of a try is something called a suffix try. So what we do in a suffix try is we take the set of words that are given to us and we expand it to include all the suffixes, right? So supposing I take a word like this, A, B, A, B, A, then the suffixes are the word itself, okay? Then the word dropping the first letter, so B, A, then just A, B, then A, B, then B, A, and finally A, and then there is an empty suffix, there is always an empty suffix. So this set is the set for which I want to build a try, right? So if I build a try for this, so a suffix, the suffixes of S are the set of all words such that there exists some other word V such that V followed by W is S, right? So I'm assuming for now, just for simplicity, that my capital S consists of a single word S. So I'm building the suffixes of a single word, right? So here is a try, for instance, for this set, right? So here is the thing for the empty word, right? So I have a dollar right at the top saying that after reading no symbols, I reach the end of the word. Here is the suffix A followed by dollar, right? The next suffix is BA. So here is BA followed by dollar. The next suffix is ABA, that is ABA followed by dollar. So you can check that every suffix that we have in our word is actually in this suffix try. So as before, what we do is we take the suffixes and we append a dollar, or rather we append a dollar and then take the suffixes. So because remember that if I put W and I put a dollar at the end, then every suffix will automatically have the dollar. So I don't have to keep on adding the dollar, right? So I use a dollar to mark the end of the word, and then I build a suffix for the try for that by examining every suffix. We'll see how to do that, right? Now what can we do with a suffix try? Well, in the earlier case, remember that what we checked was that the word that we had was either a complete word if it ended with a dollar, or we could at best check if it is a prefix, right? If it starts at the root and comes down and then our search terminates, not because we have not got a successor but because we did not reach a leaf node, then we said okay, this is a partial match, but it's always a prefix, right? It's the prefix of some word. So if I want to know whether the word occurs anywhere in a word in my set, then it need not be a prefix, just a substring, right? So with a suffix try we can answer that question, is W a substring? We can also answer questions like this: how many times does it occur as a substring, and which is the longest repeated substring? So these are some of the questions that we can answer. So with a suffix try we can answer more questions than we can with a vanilla try, which just keeps track of the words themselves. So let's look at this particular suffix try. So we ask, for instance, for substring. So we ask whether A, B, A, B, A is there. So as usual what we do is we say A, B, A, B, A, right? And since I am able to process this, it is a substring. On the other hand, if I try B, A, B, B, I will say B, A, B, and then I get stuck. So I cannot finish processing the word. So when I cannot finish processing the word, then I know it's not a substring. So why does this work? Well, because a substring is something which is sitting somewhere inside the word. But I know that I have every suffix. So there is a word corresponding to this suffix in my suffix try. So wherever my substring starts, it defines a suffix of my word, and that suffix is represented in my try. So there will be a path for that suffix, and this word, if it is a part of that suffix, if it is a substring, it will process part of it and stop. So that's why every substring will actually be represented, because it will be the prefix of some suffix, right? So every suffix is there. So if I start where the substring is supposed to start, right? So for instance, if I look at a valid substring of this, so like AAB, then AAB, right, is part of this prefix, is part of this suffix, right? So I would find it by looking at AAB. So there is a longer part of it, but I am not worried about that. I am only looking for substring. So this is how we would find substrings, and this is why the substrings will always be found correctly. Now if I want a more like the earlier normal try would tell us about prefixes, we can also check if it is suffix by asking whether after I have matched I can see a dollar at the next position, exactly as we did for the complete match. So for instance, if I see BAA, then I want to see a dollar after this, but there is no dollar after this. So the word does not, it cannot end in BAA. Whereas if I do ABA, then though there is an extension down, there is also one way of stopping here, because one of the successors of that ABA node is a dollar. So by looking for a dollar immediately after the match among the successors of the matching node, I can check whether or not this substring is actually a suffix of the string. Then we also said about number of occurrences. So supposing I want to know the number of times that ABA occurs. So I come down to ABA. Now every time it occurs, right, there will be a completion. If it occurs only once, there is only one way of completing ABA, but if it occurs twice, so in this case ABA occurs here and ABA also occurs here. It occurs in the beginning and at the end. So if you look at the node for ABA, then the completion where ABA is the tail end substring is just an immediate dollar, whereas the completion where is the initial thing is another ABA followed by dollar. So in other words, you look for the number of leaf nodes. Remember, a leaf node in a try denotes a complete word. So you look for the number of completions of this substring, and that tells you how many times the substring occurs, because every completion of the substring will represent a different suffix. Right? So that's one way of checking. So in this case, because this ABA has two leaf nodes below the ABA node, I can get that this ABA has two extensions in my word, so it has two occurrences. And by the same logic, you can ask which is the longest such word, right? So here if we look at this, for instance, here is a word BA which has two below it. Here is another one A which has two below it, right? And finally we have the one that we found earlier, ABA, which has two below it. Now you can check that if you stop anywhere else in this, right, there are, of course technically this also has two below it because it has, so yeah, so we will not count the empty word because the empty word has every word kind of, it matches every pattern. So non-empty words is what we are looking at. So you look at any other position, like if you stop here, you have only one leaf below it. You stop here, you have only one leaf below it. So the only positions are these branching positions, right? It's not a coincidence that the trie branches here, the trie branches here, and the trie branches here. So we look among the branching positions, which is the lowest one. So we again get that not only does ABA have two occurrences as we calculated, it is also the longest substring which has more than one continuation. Right? So we are not asking for the maximum number of continuations that we could have got by counting. We are asking for which is the longest one. So we will look into the depth of the node which has more than one leaf below it. So these are all various interesting questions that you can answer about your fixed text using a suffix tribe, which is expanding your set of words by all the suffixes. So we can do a simple extension of our earlier construction of a trie to build a suffix trie. So here, as we have assumed, we are doing it with a single word. So we will assume that the constructor takes as input one word, and what it does, as we said, is we expand the word by adding a dollar to it. And now we have to look at all the suffixes. So we have to look at S0, S1. So these are the slices starting at different starting positions up to the end. So for every I starting from 0 and going up to n minus 1, right, I start at the root and I go through the entire thing and I do the same thing that we did earlier for adding. We just add it to this trie. So we are just processing every, so this is just making sure that I get every suffix by taking every starting position in the range 0 to length of s minus 1. Now once we have built that, then we have this function below called follow path, which does what we did before, right? It takes an input and it tries to trace the path in the suffix trie and tells us what is the status of that thing, right? So if I bail out in between, I return a none. So what happens here is if I am not able to execute this word in my suffix trie, if at some point I get stuck, then I return a none. Otherwise I go to the end and I return whatever I have got. Now this whatever I have got, I can analyze. So have I reached the end or have I not reached the end? So for instance, if it finds a path, okay, at all, that is the answer is not none, then I have found a substring. Right? This is what we said before. As long as I can process the entire string and not get stuck, I have found a substring because every substring will occur as the beginning of some suffix. On the other hand, if I want to check if it is actually a suffix, then not only must it be a substring, but when it finishes, there must be a dollar following it, right? So I will have to say not only that I have reached a node which is not the none node, I have not bailed out in the middle of follow path, but the node that I have reached has dollar as one of its keys. Now remember, it could have not dollar also, as we saw those things which had B and then or A and then had a dollar here and then a B below and so on, right? So we do have nodes like this where I could stop here, and it could be that it has a valid extension as a longer suffix, but it also stops here as a terminating suffix. So I just want that among my successors I have dollar. So it just says that among the keys that I see at the node where I stopped, one of the keys is dollar. Right? So this is a very simple implementation of suffix tries. So we said before that one of the drawbacks of suffix tries compared to say using a hash or a dictionary to maintain a key value store is that it is big. So let's look in particular for suffix tries, how big can a suffix trie be? So supposing I start with one word of length n, okay. So can I have a suffix trie which is as long as n, and this is easy. So if I just have a word with n copies of the same letter, then there are n suffixes from 0 to a to the power n. So each of these represents a different node in my trie. So I have this kind of a spine which is the length of my word. But notice that in general, if I have n letters, right, then we have, as we said, n suffixes, because we can chop off the first letter, chop off the first two letters, chop off the first three letters. So there are order n suffixes. And we said at the beginning that the problem with the trie blowing up happens when these suffixes don't share a good prefix. So they all kind of form lots of paths. So the question is, can I actually end up with n square such things? That is, each of those suffixes, n suffixes, essentially creates a new set of nodes proportional to n. So here is an example. So we have n a's followed by n b's. So here, for instance, is a cube, b cube. Now what are the suffixes of this? Well, we have the empty suffix, of course, but we have b, then we have bb, then we have bbb, then we have abbb, aabb, and aaabb. And now you will see that there are very few common prefixes. So here is the path for b, bb, and bbb. So what we have not drawn is all those dollar nodes. So there is a dollar node sticking off these things, and there are dollar nodes sticking off all these b's as well. Right? So a followed by 3 b's as a dollar, a followed by 3 b's as a dollar, and 3 a's followed by 3 b's as a dollar. So there are 6 suffixes. So there are these 6 dollar nodes that we have not drawn. But in addition to that, what do we have? Well, we have, because of this n b's, we have one suffix here of length n, right? And then for each of the a's, we have that same suffix, right? So we have n here and we have n here. So we basically end up with n square nodes because each of these suffixes is n times n. So it is actually n by 2 times n by 2 if you think of the overall length is 2n, right? So in terms of this n, if you think of n as the entire length of the word, it's n by 2. But basically you have n suffixes corresponding to the n a's, and each of those n suffixes has length n, right? So you end up with n square nodes. So you can have a kind of worst case suffix trie in which you have as many nodes as there are suffixes letters. But this is something that we already knew, that suffix tries are not very space efficient. So to summarize, a trie is a useful way to pre-process a fixed piece of text, and this is a very common occurrence. As we said, in principle an internet search engine is doing this, right? So it's actually maintaining information about a corpus of documents at some snapshot in time, and then your queries are with respect to that snapshot. Now it might update this corpus once in a while, but it's not going to do it instantaneously. It's not, so when you give a query to a search engine, it's not going out and searching in real time for documents. It's searching against this pre-processed index. Now there are many more things that go into this indexing, and this is not part of what we are looking at, but this information retrieval is basically a way of taking a fixed piece of text and transforming it into a representation, a data structure which you can query efficiently, and a trie or a suffix trie is one of the starting points of doing this. So the advantage of doing this is, then once you have pre-processed it, as we see, searching for a pattern, a string, takes time proportional to the length of the string. You just have to run down the trie. You don't have to do anything with the rest of the trie. So therefore searching becomes proportional to what you are looking for rather than what you are looking at, which is what is happening in our dynamic text. In our dynamic text we had to search all over the place for it, but by pre-processing we are able to search for it once and for all by just going through the pattern once, right? So suffix tries are an improvement on tries because we can make more expressive searches. As we said, we can look for arbitrary substrings, we can look for the number of times a substring occurs, and so on. And overall the main drawback that we find in using tries is the size. So there are ways of compressing tries, but then if you compress a trie but the trie is going to change, then you lose something. So it's not always clear that compressing a trie will help in a static sense, but if you have to update the trie, then you might have to blow it up again and so on.